To illustrate the application of the F-test for Pooled-OLS versus fixed effects, we will continue with the same Grunfeld example, dataset and model that we used in previous tutorials. The Grunfeld data being used here is a balanced panel containing data on 10 firms or cross-sectional units and a total of 200 observations. Earlier, we illustrated the application and interpretation of fixed effects model with individual specific effects. Therefore, we will use the same model with individual specific effects to illustrate the F-test. We know that the fixed effects model, whether LSDV or within estimator, should be applied only if the individual specific or time-specific effects are significant. Therefore, this F-test compares the results of the Pooled-OLS and fixed effects model to determine whether including the individual or time-specific effects improves the fit of the model significantly. If the individual or time-specific effects are significant, then we know that including the fixed effects will significantly improve the fit of the model. In that case, we should apply the fixed effects model. If the individual or time-specific effects are insignificant, then the model fit will not improve significantly with fixed effects, and we should prefer the Pooled-OLS model. The equation shown here is used to estimate the F-statistic for our model considering individual specific effects. The RSS refers to the residual sum of squares of the restricted model. The restricted model will be the Pooled-OLS model in this case. RSSUR means the residual sum of squares of the unrestricted model, which will be the fixed effects model with individual specific effects in our example. In this formula, I is the total number of cross-sectional or individual units. In our Grunfeld example, this will be equal to 10 because we have 10 firms in the dataset. N is the total number of observations, which will be equal to 200 in the Grunfeld data we are using. K is the number of parameters in the fixed effects model excluding the constant and will be equal to 2 because we have 2 parameters for value and capital. The I-1 equals 9 in the numerator is the numerator degrees of freedom for the F-test. On the other hand, the N-I-K equals 188 is the denominator degrees of freedom for the F-test we are applying. It is important to note here that these degrees of freedom are for the fixed effects model with individual specific effects that we are considering in our example. The formula and the degrees of freedom will be slightly adjusted in case of a fixed effects model with time-specific effects and a two-way fixed effects model. For a fixed effects model with time-specific effects only, the formula and degrees of freedom will be adjusted as shown here. The numerator degrees of freedom will be T-1 instead of I-1. Therefore, if we were to apply this F-test on our Grunfeld data, but for fixed effects with time-specific effects, then T-1 will be equal to 19 because we have data on 20 time periods. The denominator degrees of freedom will be N-T-K and will end up being 178. For a two-way fixed effects model, the formula and degrees of freedom will again be slightly different as shown here. Since a two-way model will include both individual and time-specific effects, we need to adjust for both. The numerator degrees of freedom will be I-1 plus T-1. This will end up being 28 if we were applying this F-test to a two-way model on our Grunfeld data. Similarly, the denominator degrees of freedom will be the same as the residual degrees of freedom of the fixed effects model. This will be equal to N-I-T-K plus 1 and 169 in case of a two-way fixed effects model on our Grunfeld data. Therefore, we have to be careful and adjust the degrees of freedom according to the type of effects that we are considering in the model. This F-test for Pooled-OLS versus fixed effects is easy to apply in R. We can use the pf-test command provided by the PLM package to apply this test. First, we have to estimate the fixed effects within model and the Pooled-OLS model using the PLM function as shown here. The first command is used to estimate the Pooled-OLS model and the results are saved in the Pooled-OLS object. The second command is the one we use to estimate the fixed effects within model with individual specific effects in the tutorial on fixed effects. The results are saved in the within IND object. Now that we have estimated and saved the results of the Pooled-OLS and fixed effects models, we can use the pf-test function to compare them. In the pf-test function shown here, we have to first specify the object containing the results of the within model, followed by the Pooled-OLS model. The function will automatically figure out which effects are included in the fixed effects model. For example, the function will know that we only have individual specific effects in the within IND object and apply the appropriate f-test and degrees of freedom. For only time-specific effects or a two-way model, we simply have to change the effect option to time or two ways while estimating the fixed effects within model. Alternatively, we can also directly apply the f-test using the pf-test function without estimating the models separately. In the pf-test command shown here, we directly mention the dependent and independent variables like we would do while estimating the models. We mention the data as Grunfeld and the effect as individual. This will give the same output as the earlier procedure, as the function will estimate the Pooled-OLS and fixed effects model behind the scenes and then report the f-test automatically. We can easily adjust this function for time-specific effects or a two-way model. We simply change the option effect to time for time-specific effects only and two ways for both individual and time-specific effects. Stata does not provide any command to directly estimate this f-test. The results of the f-test are automatically reported along with the model when we apply the fixed effects within model using xtreg. However, there is one disadvantage to this. Remember that Stata does not provide an option to include time-specific effects in the xtreg command. We can only include time-specific effects using dummy variables similar to LSDV approach. As a result, we cannot directly obtain this f-test in case of time-specific effects or a two-way model. Even if we include time-specific effects using I.year, the f-test reported by the xtreg command uses incorrect degrees of freedom. It does not make the degree of freedom adjustments needed for time-specific and two-way effects. However, we can apply a different version of the test based on a walled type of test. We use the LSDV model to apply this test in Stata. Remember that the LSDV model includes the individual and time-specific effects as dummy variables in the model. As a result, the LSDV model estimates additional coefficients for the individual and time-specific effects. We can use this information to test whether the coefficients of these individual and time dummies are jointly zero in the LSDV model. First, we estimate the LSDV model using the regress command shown here. The I.firm is used to include the individual specific effects using dummy variables in the model. Then, we use the testparm function as shown here and include all coefficients of dummy variables under I.firm. It is important to note here that we do not include the coefficients of other independent variables value and capital in the test. We test the hypothesis that the coefficients of all the dummy variables under I.firm are zero. That is, under the null hypothesis, all the individual specific effects are zero and we should apply Pooled-OLS. To test for time-specific effects, we can include the time dummies using I.year in the regress function. Then, we apply the testparm in a similar manner by testing all coefficients of time dummies. The null hypothesis would state that all the coefficients of time dummies are jointly zero. For a two-way model, we can simply include both I.firm and I.year and test all the coefficients of dummy variables jointly. The results of the f-test for our Grunfeld example with individual specific effects are shown in the table here. The R output for the pf-test function reports the f statistic as 49.177, df1 for numerator degrees of freedom as 9, df2 for denominator degrees of freedom as 188, and the p-value. The null hypothesis states that the individual specific effects are not significant, so we should prefer the Pooled-OLS model. The effects are significant under the alternate hypothesis and we should prefer fixed effects model in that case. In our example, the p-value is less than 0.05, so we know that individual specific effects are significant and the fixed effects model is more appropriate as compared to Pooled-OLS. The model results from the xtreg command and Stata also report the exact same statistics for this. The f-test statistic, degrees of freedom and p-value are reported exactly the same along with the model results. We know that we can apply this f-test directly in case of time-specific effects as well as the two-way model. The results of both the tests are shown in the tables here. For time-specific effects only, the f-statistic is 0.23451, df1 is 19, df2 is 178, and the p-value is 0.9997. You will notice that the degrees of freedom are adjusted exactly how we illustrated in the formulas earlier. The p-value is greater than 0.05 and we cannot reject the null hypothesis. Therefore, the time-specific effects are insignificant. In case of the two-way model, the f-statistic is 17.403, df1 is 28 and df2 is 169. The degrees of freedom are adjusted exactly like we showed in the formulas earlier. The p-value is less than 0.05, which means that at least some of the effects are significant. This is expected because we already know that the individual specific effects are significant from the first test. The walled type of test after LSDV approach in Stata gives us the exact same results as these f-tests with time-specific effects and two-way effects. Therefore, even though Stata does not give us a direct option to apply the f-test with time effects and two-way models, we can still estimate it with correct degrees of freedom manually using the LSDV model and test-parm function as shown earlier in this tutorial. Thank you for watching, and I will see you in the next tutorial.